Hi everybody, welcome to another video in Linear Algebra, section 4.4, coordinate system. First, the unique representation theorem. So let B be a set of vector B1 to Bn be a basis for vector space V. Then for each x in V, there exists a unique set of C1 to Cn such that x is equal to a linear combination of B1 to Bn. So a few things here. B1 to Bn is the basis. Notice that the vector space V and x is in vector V. And since B is the basis, x can be written as a linear combination of the vectors in the basis. And the theorem says it is a unique set of scalar C1 to Cn. And of course, when we write like that, if we rewrite this in the matrix form, we put on the vector in the basis. And then on the C1 all the way to Cn. Right, we can write that in that form. Now suppose B equal to the basis, the vectors that form the basis for V and x is in V, then the coordinate x relative to the basis of B, or we just say B coordinate of x are the way C1 to Cn, and we're going to write like this. And the map x to the B coordinate of x is called the coordinate mapping determined by the basis B. By the way, sometimes we write the vector B as the script B, or just uppercase B, and it's fine. Right. Here's the first example. We have vector B1 and B2. Let that the set of those two vectors form a basis. And x is 4 and 5. Now find a coordinate of vector x in B coordinates of x relative to B, or we say find the B coordinates of x, pretty much. Right. A few things here. First, we have two vectors. They are not multiple of each other, so they are linearly independent. So linearly independent, and this is all of them are vectors in R2. So B1 and B2 together will form the basis for R2. So originally we have standard basis. For R2, of course, those are the columns from the identity matrix. And now we can use the new basis to represent the point x, and according to that theorem, that representation is unique. So pretty much we just solve the equation. The linear combination of the basis, the vector in the basis, is equal to x. So write that in the vector form: B1, B2 times C1, C2 equal to x. And now put the numbers in. Vector B1 is 2 and 1. Vector B2 is negative 1 and 1. C1 and C2 to be found. And vector x is 4 and 5. And we just put everything in and do the reduced row echelon form. And that's what we have. 1, 0, 0, 1, and then 3 and 2. So we have C1 is equal to 3, C1, C2, and the pivot. So C1 is equal to 3 and C2 equal to 2. And we write vector x is equal to 3 times vector b1 and 2 times vector b2, or we can say x in b coordinates is equal to 3 and 2. That's what we have. Now let's draw it out. First, vector 4 and 5, vector x in the standard basis is 4 and 5. Now, the vector b1 is 2 and 1, 2 and 1. So that is b1. And the vector b2, negative 1 and 1. Right, now, according to the b coordinate system, we're going to have 3 times the b1, so we're going to multiply that 3 times. At 3 times b1, and then 2 times b2, 2 times b2. And when we add those two vectors together, let's just say we use the parallelogram rule. And you see, x can be represented using the linear combination of b2 and b1, in particular 3 times b1 plus 2 times b2, and that is uniquely represented by the vector 3 and 2 in the b coordinates. So that's all we have for this example. Now, a little more terminologies. If we write x as a linear combination and put all the vectors b1 to bn into the matrix, that called b p of b pb, called the chain of coordinates matrix from b to the standard basis Rn. Since they form the basis, it is invertible, and so we can take the inverse, and that's what we have. And the inverse is certainly, of course, invertible as well. So the map is 1 to 1 and on 2. So we have x in the standard basis, go to x in the b coordinate, and then from b coordinate we can go back to the standard basis, and that's essentially what we have here, of course. And all the terminologies, we can, such as in general, 1-to-1 linear transformation from V onto a vector space W is called isomorphism from V onto W. So that means what we have in V, if we add them, the vector will be added in the vector W as well. Right, and that was exactly we say that every vector space calculation in V is accurately reproduced in W and vice versa. So what we do on this side is the same thing on the other side. Right, now we just have another example, just like what we did in the first example, but this time it is vectors in R3, and we only have two vectors V1 and V2. So that's certainly V1 and V2 cannot span the whole space V3, but only a subspace, so H is a proper subspace, so it's not equal to R3, but it is a subspace of R3, because those these vectors once again are linearly independent. They are not multiple of each other, so this will be the basis. Right, now determine if x is in H, and if it is, find the b coordinates of x. So simple enough. So if it is a linear, if it is in H, I just write if X in H, then X can be written as a linear combination of the vectors in the basis. And I'm going to write this in the matrix form. And just put the numbers in. Vector X. And do the reduced row echelon form. Should be 3 by 3, sorry. Right. So C1, C2. So we have C1 is equal to 2 and C3 is equal, C1 is equal to C2 is equal to 3, sorry. So we can say X is 2 times vector V1 and 3 times vector V2. Or we can say X in the coordinates, in the B coordinates is 2 and 3. Yeah, we have the graph here in R3. Right. So pretty much now in this section we learned that we can represent X in the linear combination of the vector in the basis. Of course, if X belongs to that space, and if we have the basis, we can represent uniquely the point X, and we just solve the system equation for the ways C1 to Cn. So simple enough. But that's all we have for this section 4.4. As always, thank you for watching and see you in another video in linear algebra.